guys, Mrs. Traver here. Today we're going to talk about angles and arcs and circles. Your learning target for today is that you can identify central angles and inscribed angles and solve for their relationship. You know you'll be successful when you know that the inscribed angle and the measure of its corresponding arc are the same. Let's jump in and first remind ourselves of what central angles are. So we've got central angle STU here. This is called the central angle. And then we also have arc SU, and they have a relationship. The measure of an arc is equal to the corresponding central angle. So let's work it out and see what it looks like in real life. So if we know the measure of SU is, we'll say 45 degrees. So this is the arc, from here to here is 45 degrees. It's equal to its corresponding central angle. So its corresponding central angle, we'll call this one angle STU, is also 45 degrees. So that's the measure of angle STU is 45. We can do it for the other parts as well. So we've got the major arc, which is arc STU. We'll do that in a different color. So that's from here all the way around to here. Would be 360 minus 45, so 275. And SZU is the same, 275. Let's move on and try some other ones. Let's look at these arcs. So it says major arc is NQM, so NQM. So the major arc for it would be NLM. So NLM, and we'll put an arc above it since it says major arc. Now let's try angle ZQX. ZQX, that's this angle. We want to find an arc made by it. It would be this arc, arc XZ. Since it didn't say major arc, I can assume it's the minor. Here's another one. We've got arc FDE. So it goes from F over to D, then to E, from here to here. So we can use angle FQE. Now let's try the next one, arc ZXY, Z, then to X, then to Y. So from here all the way to here, and that corresponds to angle ZQY. Let's look at some other things here that are kind of interesting, I find. So these are actually used in order to find the circumference of the Earth. So here's a little picture. I want to show you how in the world this happened, because at some point we measured the circumference all the way around the Earth and we used this math we're learning to do it. So here's a picture of the Earth, and if you could go into its core and look at its cross section here, this is the circle made by the Great Circle of the Earth. And what really happened is there was someone who put a stick right here and looked at the shadow based on where the sun was. Then they moved the stick until there was no shadow, and they found with trigonometry and arc length the length of this arc, and then they were able to figure out reasonably how big that arc was compared to the whole circle, and therefore find the circumference. I want to show you what this looks like in a little video, so let me pause myself here so you can see what's going on.
In the mid-20th century, we began launching satellites into space that would help us determine the exact circumference of the Earth, 40,030 kilometers. But over 2,000 years earlier in ancient Greece, a man arrived at nearly that exact same figure by putting a stick in the ground. That man was Eratosthenes, a Greek mathematician and the head of the Library of Alexandria. Eratosthenes had heard that in Syene, a city to the south of Alexandria, no vertical shadows were cast at noon on the summer solstice. The sun was directly overhead. He wondered if this were also true in Alexandria. So on June 21st, he planted a stick vertically in the ground and waited to see if a shadow would be cast at noon. It turns out there was one, and it measured about 7 degrees. Now, if the sun's rays are coming in at the same angle at the same time of day, and a stick in Alexandria is casting a shadow while a stick in Syene is not, it must mean that the Earth's surface is curved. And Eratosthenes probably already knew that. The idea of a spherical Earth was floated by Pythagoras around 500 BC, and validated by Aristotle a couple centuries later. If the Earth really was a sphere, Eratosthenes could use his observations to estimate the circumference of the entire planet. Since the difference in shadow length is 7 degrees between Alexandria and Syene, that means the two cities are 7 degrees apart on Earth's 360-degree surface. Eratosthenes hired a man to pace the distance between the two cities, and learned they were 5,000 stadia apart, which is about 800 kilometers. He could then use simple proportions to find the Earth's circumference. 7.2 degrees is 1/50th of 360 degrees. So 800 kilometers times 50 equals 40,000 kilometers. And just like that, a man 2,200 years ago found the circumference of the entire planet with just a stick and his brain.
Alright, so credit goes to credit due at Business Insider for that little video. I thought that was kind of cool to talk about in light of today's lesson. Let's jump into our next topic, which is inscribed angles. So an inscribed angle is one that's made on the edge of a circle. So the inscribed angle here is angle ADB, and notice it has two endpoints on the circle and the vertex on the circle as well across from it. So here's the rule, is that the measure of ADB, which is right here, I'll label it in blue so we can see with colors, is equal to half of the measure of arc AB, which is over here. Let me go a different color so we can kind of get it all labeled. So for example, what we could say is if this were, I don't know, 40, say, because it's half, then the other angle would be double it. So this would be 20. Let's try another. If we had the measure of angle AB is 40, then you can double it. So you can go backwards and forwards. Let's move forward. Here is inscribed angle theorem written as best as we can. So the inscribed angle BDC intercepts arc BC. So notice we've got the central angle here and the inscribed angle. So if we know this one is x, then this one out here is 2x. And there we go, so I'll put 2's here. So that's kind of our setup for each of these. Let's try it here. So find the measure of the indicated angle. The first one, I notice it's going to be half that. So x is 118 divided by 2, which is 59. The next one, we can double it. X equals 2 times 41, or 82. All right, let's try our next one on part D. So on this one, we've got angle Y, which is a inscribed angle, and arc X. And we've also got central angle 56. So if this is 56, so is this arc, and then its inscribed angle that goes with it is going to be half that. So 28 degrees for that guy, because it's half. Let's try the next one here. It's telling us that X is this angle here, so this angle is X, and I noticed that this angle is a central angle and it corresponds to 114, so this must be 114 as well. Our last one here, we've got a couple triangles going on, and I noticed none of them have to do with the center. However, I do have this 28 that goes to this arc out here, so this must be 56. And then to get Y, I notice Y also is a arc that goes up to 56, so Y must also be 28. So we're going to stop for today, guys. I will see you next time. Bye.